We are in section 6.3, volumes of cylindrical shells. Some volume problems are very difficult to solve by using the previous methods. For example, to find the volume of a solid obtained by rotating about the y-axis and the region bounded by y equals x plus 2 squared times x minus 1, y equals 1, and y equals 3. If we slice perpendicular to the y-axis, we get a washer. But to compute the inner radius and the outer radius of the washer, we will have to solve the equation y equals x plus 2 squared times x minus 1 for x in terms of y, which is not easy. Fortunately, there's a method called the method of cylindrical shells. It's our new method, which is easier to use in such cases. So in order to do this method, we need to know that the volume of a cylinder, which we learned back in a geometry class, is equal to pi r squared h. And this is the volume of a cylinder. And looking at the diagram here, you can see that we have a few different things labeled on the picture. So R1, if you notice, is equal to our inner radius. And R2 in the diagram is equal to our outer radius. And then delta R in our diagram is equal to that difference, or the thickness of the shell. So we also can think of it as R2 minus R1. And then R, if you notice, goes in between that thickness. So R is going to be equal to that midpoint between them. So R1 plus R2, and then dividing that quantity by 2. Let S be the solid obtained by rotating about the y-axis the region bounded by y equals f of x, where f is continuous and f of x is greater than or equal to 0. Y equals 0, x equals a, and x equals b, and where a is in between b and 0, and it could equal 0. And so the volume of a solid in the figure above is attained by rotating about the y-axis the region under the curve y equals f of x from a to b is going to be given by, and so in order to come up with this equation, we're going to do a little bit of work here to see this. So we're going to say the volume would be equal to that outer volume minus the inner volume. So I'm going to call it V2 minus V1 since we are using 1s and 2s in relationship to inner and outer. And the volume of the outer cylinder would be equal to pi r2 squared times h minus the volume of that inner cylinder is going to be pi r1 squared h. And I'm going to go ahead and factor out my pi and also my h. So I'm going to have pi, and then I would have r2 squared minus r1 squared, and then times h. And then we know that we can factor r2 squared minus r1 squared, and when we do that, we have r2 minus r1 times r2 plus r1 times h. And then we know that we have r2 minus r1, and that is just equal to our delta r. And then looking at what we have here as r2 plus r1, I'm going to do a little work here, and I'm going to put a 2 in, and I'm going to multiply and divide by 2, so it's like doing nothing. But we're going to have v is equal to pi, and I'm going to multiply by 2, so I'm going to put times 2. And then I have delta r, and then over here I'm going to do r2 plus r1 divided by 2, and then times h. So what I did here was I multiplied and divided by 2. So mathematically that doesn't change what we have written there. But that expression that I have here, and I'll box it, is going to be equal to r. So this is going to be equal to 2 pi r h times delta r. And so in order to find our volume, we're going to have to integrate from a to b. And our formula is going to be, and I'm going to write this not in terms of r, but in terms of x. We're going to have 2 pi x times f of x, which would be that height, times dx. And this again is for a greater than or equal to 0 and a less than b. And again, getting that formula from what we just derived on the side. So the best way to remember the formula is to think about a typical shell, cut and flatten it out. In the figure below, with the radius x and a circumference of 2 pi x, a height of f of x, and the thickness is going to be delta x or dx. And so looking at the picture right below, if you had that cylindrical shell and you cut it and you open that up, this would have been the length of that shell, would have been 2 pi x, and that's our circumference, and x is equal to the radius here. And then we have the height of our shell, which is equal to f of x, and then that thickness, which is delta x, or when we integrate, we rewrite that as a dx. So right below this, we have an example. And the example says, use the method of cylindrical shells to find the volume of a solid obtained by rotating about the y-axis, the region bounded by y equals 2x squared minus x cubed, and y equals 0. And so the graph is given here, and also a diagram and a picture of what we obtained as we rotate this. And you can see what the shape would look like in that three-dimensional form as we rotate it. And so in order to find this volume, we are going to take this and rotate it around our y-axis. And so let's go ahead and try to set up this problem using the method of cylindrical shells. So our volume is going to be, from before, is going to be the integral from a to b of 2 pi x times f of x dx. And so looking at what we have here, the first thing is our height, f of x, is equal to our given function. So that would be our height, and that changes depending on that function. And then our radius we call x, as you can see in this picture. And we're going to be integrating x, our radius, and that function values, from 0 out till 2. So you can see we started at 0 and we're going all the way out till 2. And from here, I'm going to go ahead and plug this all into our volume formula. So again, we're integrating from 0 to 2. We have 2 pi x. F of x is going to be our function, which is 2x squared minus x cubed dx. You can move that 2 pi out in front of that integral. And I'm also going to multiply in the x, distribute that in. So we have 2x cubed minus x to the 4th dx. And if we go ahead and integrate this, we will end up with 1/2 x to the 4th minus 1/5 x to the 5th. And evaluating this from x equals 0 to 2. And so substituting in 2, we have 1/2 times 2 to the 4th minus 1/5 times 2 to the 5th minus 2 pi, and then substituting in 0, we just get 0. And so working this out, we end up with 16 pi over 5. So right below, so we have another example. The example says use the method of cylindrical shells To find the volume generated by rotating the region bounded by the given curves, y equals 4x minus x squared, and y equals x about the y-axis. So we're going to rotate it this way. This time I did not give you a graph, so we are going to have to graph this ourselves. It also says the area bounded by these two curves, and so I need to figure out where they're going to intersect. So I'm going to set these equal to each other. So we have 4x minus x squared equals x. And then moving everything to one side, I'm going to move everything to that right side. I end up with x squared minus 3x equals 0. I'm going to factor out an x. So I get x equals 0 and x equals positive 3. And so from here I'm going to go ahead and sketch what this graph would look like. And again, I'm rotating this around my y-axis, so I'm going to make sure that I leave some space over on the left side of my graph to rotate. And so the first equation that we have is a parabola. It is opening down. And so if you substitute in 0, 1, we have 1 comma 3. If you substitute in 2, we get 4. And then substituting in 3, we get 3. So our first graph is here. And this is going to be y equals, and we have 4x minus x squared. The second graph we have is just a linear function, y equals x. So 0, 0, 1, 1, 2, 2, and 3, 3, and you should have a straight line here. And so this is going to be y equals x. And so we're going to take this shape in this region and we're going to rotate it around our y-axis. And so if you think about one approximating rectangle here, if you draw in a little rectangle, and think about taking that and rotating it around your y-axis, the shape is going to be rotated around, and I'm just going to draw it again on the flip so we can kind of see a little bit better a visual representation of what this volume would look like. And so this rectangle would have ended up over here also. And so as we rotated this is going to make a cylindrical shell. And so in order to come up with the volume using the cylindrical shell method, we have a formula to integrate from a to b of 2 pi x times f of x dx. And this is our delta x over here is that thickness. We also need to calculate the height, or h, which is going to be my function over here. So f of x we can think of as h. And so in order to get the height of that function, it is going to be, or that height of that rectangle, it's going to be our top function minus our bottom function, just like what we saw in the last section. So for this problem, the top function is going to be 4x minus x squared minus our bottom function, which is just x, and this is going to simplify to 3x minus x squared. And so in setting up this volume problem, we're going to have the integral from, and again we're integrating from 0 out to 3 of 2 pi x, f of x, or our height of that rectangle is going to be 3x minus x squared, and then dx. Again, pulling that 2 pi out in front, you get 0 to 3, and multiplying in that x, we have 3x squared minus x cubed dx. And then integrating this, we're going to end up with x cubed minus 1/4 x to the 4th, evaluated from x equals 0 to 3. So we have 2 pi times 3 cubed minus 1/4 times 3 to the 4th, minus, and then substituting in 0, we do just get 0. And so working this out, we have 2 pi times 27 minus, and then we have 3 to the 4th, so 81 over 4. You can get a common denominator. You can also use your calculator as an aid, but your final answer should be 27 pi over 2. The next example says, use the method of cylindrical shells to find the volume generated by rotating the region bounded by the given curves y equals 4 minus 2x, y equals 0, and x equals 0, about x equals negative 1. And again, we're using the method of cylindrical shells. And so in order to do this problem, we need to sketch what the region would look like. We are rotating this about x equals negative 1, so I need to make sure to keep in mind that we will be rotating around that and making sure my graph has enough space to the left. So the line x equals 0 and y equals 0. And so x equals 0 would be our y-axis, and y equals 0 is going to be our x-axis. Kind of change the color there so we can see it. And then I need to graph the line y equals 4 minus 2x. And so when x is 0, we have y is equal to 4. At 1, we have 4 minus 2, which is 2. And at 2, we end up at 0. And graphing the line, you can use any method that you would like. So this is our region. And we're going to now rotate this around x equals negative 1. So I'm going to go ahead and make a dashed line here so I can show this. But we are going to rotate this around x equals negative 1. And so as we rotate this, my shape is going to get rotated around. So I'm going to draw it also over here the best I can. And if you think about your approximating rectangle, so go ahead and draw a rectangle on here. And as that rectangle rotates around, you'll notice that you're going to have a cylindrical shape. And we're using the method of cylindrical shells to find the volume. And so just like what we saw before, the height is going to be equal to the height of that function, since this time we're only dealing with one function and it's then laying on the x-axis. That height is going to be equal to 4 minus 2x. So just by that function. And then we need to think about the radius of this. So this would be our radius. And if we go back and we look at the last example that we had, so I'm going to scroll back up here, the radius that we had that I didn't mark on here was just this distance here. We called this radius just equal to x. But for this problem, we don't have it set up the same way, since we're not rotating around the y-axis, we're rotating around x equals negative 1. That radius is going to be the distance that we have is x, that we would have for this little part here. And then also that distance before it, which was negative 1. And so we're going to do r is equal to x minus negative 1. So our radius is going to be equal to x plus 1. And so in order to write down our volume, our formula is going to be the integral from a to b of 2 pi, and I'm going to write it as r h dx. And so our volume is going to be the integral from, and we are integrating, our function is just going from 0 out to 2. So we're integrating from 0 to 2 of 2 pi r, our radius is x plus 1, and h, our height, is going to be 4 minus 2x dx. So in order to integrate this one, I'm going to pull my 2 pi out in front, and then I'm going to multiply out x plus 1 times 4 minus 2x, and combine my like terms. I arrive at negative 2x squared plus 2x plus 4 dx. And then integrating this, we have negative 2/3 x cubed plus x squared plus 4x, evaluated from x equals 0 to 2. And so then substituting in 2, we get negative 2/3 times 2 cubed plus 2 squared plus 4 times 2. And then substituting in 0, we just get 0. From here, we can simplify this and combine our fractions together, but we end up with 2 pi times negative 16 over 3 plus 4 plus 8. And working this out, again, getting a common denominator or using your calculator, we arrive at 40 pi over 3. So we have 2 more examples that we will look at together. One, we're going to be rotating about the axes, the x-axis, and the other one on the next page, we're rotating around x equals 5. And so both of these are going to go ahead and circle, and we'll work on these together in class.